Welcome back to the course on pericyclic reactions and organic photochemistry. We are in module 7 of the course now. In this module we will start with cycloaddition reaction. Cycloaddition reactions are extremely important reactions because they are ring forming reactions. They are very widely used in organic synthesis. We will see in a few modules how the cycloaddition reactions are useful in organic synthesis. In this module we will introduce the cycloaddition reaction, derive the Woodward Hoffmann rules for the cycloaddition reaction, and also consider some 2+2 cycloaddition reactions, which are the simplest of cycloaddition reactions one can think of. By definition, addition reactions of two molecules leading to the formation of a cyclic compound is called a cycloaddition reaction. Cycloaddition reactions are essentially ring forming reactions, so they are very useful in formation of rings of various sizes. The reverse reaction is known as cycloreversion or the ring cleaving reaction. Some of these reactions are reversible. They do undergo cycloreversion. One must understand that when we are dealing with pericyclic reaction, we should be in a position to distinguish those cycloaddition reactions which are pericyclic, concerted in nature, and those which are not pericyclic and non-concerted in nature. Not all cycloaddition reactions are pericyclic or concerted in nature. This is something one can see very clearly in the next two slides by various examples. Some cycloaddition reactions essentially proceed through diradical intermediate or ionic intermediate, which are known as the zwitterionic intermediate. Pericyclic cycloaddition reactions are essentially those reactions which proceed in a single step with no intermediate, which is the basic definition of any pericyclic reaction. Now take these examples. The first example is what is known as the Paterno-Bucci reaction. This is a cycloaddition reaction of a ketone with a olefin to give a oxetane as the product. This is truly a cycloaddition reaction because it is giving a cyclic product at the end. However, this reaction is known to go through the 1,4 diradical that is shown as the intermediate in this case. So that makes this a non-pericyclic cycloaddition reaction. Similarly, the cycloaddition reaction of an enone to a olefin to the cyclobutane is known. Butane is known. This reaction is also known to undergo via the formation of the 1,4 diradical species that is shown here as an intermediate. So these are reactions which proceed through some kind of an intermediate. So they make them disqualified from the pericyclic pathway. They are not pericyclic cycloaddition reactions. Now, when the two components are highly biased in terms of their electronic nature, one being extremely electron rich, the other one being extremely electron poor in nature, they can undergo cycloaddition reaction through the formation of ionic intermediates of this type. Take the example of this particular enamine, which is nothing but N-vinyl pyrrolidine, for example, and dicyanoethylene as the other component. The cycloaddition reaction essentially gives you the cyclobutane derivative, but not in a single step, but in a stepwise process involving the formation of a zwitterion. Why is this zwitterion formed in this particular case? Because this zwitterion is particularly stable because of the stabilization of the positive charge by the nitrogen lone pair and the stabilization of the negative charge by the two electron withdrawing cyano-functional group in this particular. This is an active methylene kind of a anion is what is generated in this particular system. Instead of having an enamine, one can have enol ether. This is a ketene acetal is what the structure represents. Ketene is C double bond O. This is acetal of the particular carbonyl functional group in the ketene. So this is called the ketene acetal. Ketene acetals also undergo cycloaddition reaction with the dicyanoethylene through the formation of the zwitterionic intermediate, which are 1,4 diionic substances. This intermediate essentially collapses to give the cyclobutane derivative that is shown here. So these are examples of non-pericyclic, non-concerted cycloaddition reactions. Now when it comes to pericyclic type cycloaddition reaction, they can be classified depending upon the number of electrons that are involved in the cycloaddition step. For example, 2+2 cycloaddition reaction to form of two ethylene molecules to form a cyclobutane is a very well-known reaction. The designation that is given is 2pi plus 2pi because there are 2pi electrons involved in each of these acetylene. So the 4pi electron system is what is responsible for the formation of the cyclobutane formation. This is a intramolecular cycloaddition reaction. Both the components of the cycloaddition reactions are built in within the molecule connected by a loop of, let us say, carbon atoms in this particular case. Here is a butadiene molecule undergoing a cycloaddition reaction with an acetylene to form a bicyclic derivative. Because this is already connected by a loop, this is an intramolecular system, it should essentially give you a bicyclic compound of this kind. Note that this is a 4 pi electron system. All the 4 pi electrons are involved in the cycloaddition process. However, the acetylene, which is also a 4 pi electron system, only 2 pi electrons of the acetylene are actually involved. The remaining 2 pi are intact in the product you can see here. So this is actually a 4 pi plus 2 pi. 4 pi component is the diene, 2 pi component is the dienophile, which is this acetylene unit in this particular case. When two butadiene units undergo face-to-face cycloaddition reaction of this type, then it is called the 4 pi cycloaddition reaction. 4 pi 5 pi cycloaddition reaction of two butadiene molecule essentially give you cycloocta-1,5 diene as the product. Now here is an interesting example of diazomethane adding to a olefin to give the pyrazolidine kind of a structure. Heterocyclic compound is what is being formed here. Here the diazomethane essentially is a 4 pi electron component and the ethylene is a 2 pi electron component. The 2 pi electrons of the nitrogen double bond and the 2 electrons from the CH2 minus essentially contributes to the overall 4 electron system of the diazomethane. This is an example of a 1,3 dipolar cycloaddition reaction. One can always write this structure in the form of a 1,3 dipolar structure. This is a dipolar structure that is written, and it forms a 5-membered ring, heterocyclic. Various types of 1,3 dipoles essentially gives you various types of heterocyclic compound. These are important class of cycloaddition reaction to synthesize heterocyclic system. Finally, let us come to the largest cycloaddition reaction that is known. For example, this is heptafulvalene as the molecule. This is a 14 electron system. Overall, if you count all the electrons in this heptafulvalene molecule, there are 14 electrons, and this is a 2 electron system. So it is a 14 pi plus 2 pi cycloaddition reaction. You can see here all the 14 electrons are involved in the cycloaddition reaction by the product structure that is given here. And for the time being, let us not worry about the stereochemistry of the 2 hydrogen in this particular system. This is a 14 pi plus 2 pi cycloaddition reaction. 14 electrons of the heptafulvalene as well as 2 electrons of the tetracyanoethylene react together to form this particular cycloadduct. So these are some generic examples or the illustration of cycloaddition reactions of various kind that we will encounter in this course. If it is a simple addition reaction, when the two adding atoms, let us say 2 bromine atoms are adding to an ethylene, then you would call it as a syn addition. And if the 2 bromines are adding from opposite face of the pi system, then you would call it as an anti-addition. In the cycloaddition terminology, the addition taking equivalent to a syn addition is called a suprafacial addition. In other words, the 2 components are adding to the lobes of the pi system from the same side of the pi system. If you consider the planar pi system, the top face and bottom face can be distinguished. If both the components are adding from the same side of the lobes of the pi electron system, then it is called suprafacial. On the other hand, if one of them is approaching from the bottom, the other one is approaching from the top, then it would be an antifacial kind of a cycloaddition reaction. We will see some examples of what is a suprafacial addition and what is an antifacial addition in a few minutes. It is not only necessary how many pi electrons are involved in the cycloaddition components, it is also necessary with respect to each of the component whether it is a suprafacial or antifacial. This has to be specified in order to complete the definition of the cycloaddition reaction. For example, we will see very soon that the cycloaddition of ethylene to form cyclobutene is a 2 pi suprafacial process. In other words, both the olefins are adding to each other in a suprafacial manner. A thermal Diels-Alder reaction is a 4 pi suprafacial and 2 pi suprafacial process. In other words, the diene and the dienophile approach face to face with respect to each other, and in each of the component the addition is a suprafacial manner addition is what is taking place. So this kind of a complete description of a cycloaddition reaction not only gives you the number of pi electrons and the number of components involved, it also very clearly tells you what is the nature of overlap between the molecular orbitals of the components, whether they are suprafacial, antifacial with respect to each other. Now, the cycloaddition of ethylene to form cyclobutene is a 2 suprafacial process is only under photochemical condition, whereas this is under thermal condition. This is based on the Woodward Hoffmann rule that we will be deriving very soon for the cycloaddition reaction. Now before we derive the Woodward Hoffmann rule, the generalized Woodward Hoffmann rule is given here. The number of electrons, let us say for example, there are two components that are involved in the cycloaddition process. If you take 2 plus 2 cycloaddition reaction, then P plus Q will be 4. So 2 pi plus 2 pi corresponding to 4 electron system, or you can have a 4 pi plus 4 pi corresponding to an 8 electron system. All of them are 4n electron system. On the other hand, you can have a 4n plus 2 electron system, 4 plus 2 or 6 plus 4 for example. These are all 4n plus 2 kind of an electronic system. Now under thermal conditions and the photochemical condition, the Woodward Hoffmann rule allowedness as well as the forbiddenness of these reactions are very clearly defined in this particular table. For a 4n electron system to undergo a thermal addition, one of the component has to be at least the antifacial component. If both of them are suprafacial component, it is not an allowed process, it is a forbidden process. However, under photochemical condition, both the components are suprafacial with respect to each other, then only it is allowed. If one of the component happens to be an antifacial component, then it will be a forbidden process. We will use the various methods of analyzing the pericyclic reactions for the cycloaddition reactions also and derive this Woodward Hoffmann rule. Now once the Woodward Hoffmann rule for the 4n electron systems are defined, defining the 4n plus 2 electron system is not difficult because they are complementary to each other. What is good for the allowedness under thermal condition will be a forbidden process in the case of the 4n plus 2 system. For example, here one of the component is an antifacial component. When it is in the 4n plus 2 kind of a system, that is a forbidden process, whereas here it is an allowed process. What you need to remember essentially to follow this lecture is that the 2 pi suprafacial, 2 pi antifacial is a thermally allowed process. Whether it will take place or not, we will see in a few minutes. The 2 pi suprafacial where both the components are suprafacial with respect to each other is a photochemically allowed process. The 4 pi suprafacial and 2 pi suprafacial is a thermally allowed process. This is the Diels-Alder reaction that we are talking about. Similarly, the photochemical Diels-Alder reaction, one of the component has to be antifacial. The 2 pi component or the 4 pi component has to be antifacial with respect to each other. Now let us say for example the frontier orbital method usage for the derivation of the Woodward Hoffmann rule. Let us look at it. If two ethylene units are coming parallel to each other, like a sandwich for example, it can form a cyclobutane. Under these conditions, the overlap of the orbital is shown in this particular case. This is the highest occupied molecular orbital of one of the ethylene, and this is the lowest unoccupied molecular orbital of another ethylene. And essentially the orbital interaction, if you see, these two lobes are interacting with these two lobes during the course of the reaction in the transition state. In other words, with respect to this pi system, it is suprafacial because the two lobes are on the same side of the pi system. Similarly, these two lobes are also on the same side of the pi system. So both the components are suprafacial and suprafacial with respect to each other. However, in the ground state, the homo-LUMO interaction essentially leads to an antibonding kind of an interaction, which is shown by the overlap of this molecular orbital lobe with this molecular orbital lobe. Such an antibonding interaction will cause energy, and as a result of that, we can say that this is a thermally forbidden reaction. However, under photochemical condition, you are promoting one electron from the ground state to the excited state. So the HOMO of the ethylene actually is similar to the LUMO of the ethylene, because this is an excited state ethylene we are talking about. In the excited state ethylene, in the ground state ethylene, you have a HOMO with 2 electrons. In the excited state ethylene, you have the highest occupied molecular orbital with 1 electron and the lowest ground state molecular orbital with 1 electron each. So the HOMO, the HOMO of the ethylene is essentially having the same symmetry as the LUMO of the ethylene. So this is the ground state LUMO and this is the excited state HOMO of the ethylene molecule. Here again the bonding is suprafacial with respect to this ethylene and suprafacial with respect to this ethylene also. You can see here this overlap is a bonding type of an interaction. This overlap is also a bonding type of an interaction. So this is a perfect combination of overlap with the bonding interaction of both the lobes in forming the sigma bond of the cyclobutane, and hence this is a photochemically allowed process because one of the ethylene has to be in the excited state, electronically excited state. It's possible to have one of the ethylene in the electronically excited state only under photochemical conditions. The HOMO-LUMO interaction is essentially 2 pi suprafacial, 2 pi suprafacial and 2 pi suprafacial and 2 pi antifacial cycloaddition reaction. That is, This picture corresponds to the HOMO-LUMO interaction being a 2pi suprafacial with respect to one component and 2pi anterofacial with respect to another component. The top picture shows you the 2pi suprafacial overlap. The bottom figure, if you look at, this is suprafacial with respect to one of the component here, and it is anterofacial with respect to the other olefinic component. For example, this lobe and the opposite side lobe is what is interacting with this. Although geometrically it is not feasible for this lobe to interact with this lobe when the two molecules are approaching parallelly, conceptually one can think of this to be a anterofacial kind of overlap with respect to this ethylene, suprafacial kind of overlap with respect to this ethylene. With the parallel approach, it is thermally allowed process, but geometrically not feasible to overlap the orbitals in this particular manner. Going from the bottom to the top of the orbital is not possible in terms of the overlap. So geometrically this is not an allowed process, although Woodward Hoffmann rule wise you would say that this is an allowed process. The problem is that these two olefins are approaching parallel with respect to each other. So suprafacial is the most convenient way of overlapping. Suprafacial anterofacial overlap is not a convenient way because it is geometrically this orbital is far away from this orbital. So overlap will not be possible. So what if the two ethylenes are approaching perpendicular to each other instead of parallel to each other? That will give you a twisted cyclobutane as the product in this case. And this is a orbital pictorial representation of the perpendicular approach. This is the horizontal ethylene and this is a vertical ethylene, and the disposition of the pi bonds are very clearly shown here. Now with respect to the horizontal olefin, if you look at this top molecular orbital, the top lobe of the molecular orbital and this top lobe of this molecular orbital is what is interacting. If you look at the vertical olefin, the orbital interaction is between this lobe and this lobe, and this lobe and this lobe. So with respect to the vertical olefin, it is anterofacial very clearly because this lobe and this lobe are not on the same side of the plane of the ethylene. This is in opposite side. So with respect to the vertical olefin, this is an anterofacial process. With respect to horizontal olefin, it is a suprafacial process. Although this looks like geometrically feasible, this is geometrically highly crowded because of the hydrogens will poke with respect to each other. These hydrogens will essentially come in the way of this sigma bond here. So although it is geometrically it is a thermally allowed process, but geometrically it never happens because of the fact that it's a highly steric, geometrically crowded system is what we have in this particular system. However, you will see that later on, ketenes do undergo cycloaddition reaction in this manner. The 2pi suprafacial, 2pi anterofacial is the mode of cycloaddition for ketenes. Ketenes are special cases because the central carbon atom is an sp carbon without any substituents being present there. So that will not have any kind of a steric interaction when it undergoes a suprafacial anterofacial kind of overlap, which we will see in a few modules later. Now what happens to a 4pi 2pi cycloaddition reaction? This is the HOMO of ethylene and LUMO of butadiene, or you can take the HOMO of butadiene and LUMO of ethylene. It doesn't matter in this particular case. Both these overlaps are isoenergetic in nature. We'll see it in a few minutes. And this is a thermally allowed process. You can see here suprafacial with respect to the diene because this lobe and this lobe is interacting. Suprafacial with respect to dienophile also because the same side lobes are interacting with the butadiene unit. Same is the picture here. This is suprafacial with respect to the diene. This lobe and this lobe are interacting. Whereas this is also suprafacial with respect to the dienophile ethylene, where the two lobes on the same side are interacting. You can see such an interaction essentially leads to bond formation. Bonding type of an interaction is what we have. So the coefficients of the algebraic sign of the coefficients are essentially same between the overlapping orbital, which will lead to a sigma bond formation. And hence this kind of a face-to-face approach with the suprafacial overlap for a 4pi electron 2pi electron system is a thoroughly allowed process. On the other hand, if you take the photochemical process, one of the component has to be in the excited state. The HOMO of the butadiene is in the excited state. Butadiene is what is given here. The HOMO of the ground state butadiene is the psi2 or the pi2 with only one node here, whereas the HOMO of the excited state butadiene should have two nodes. One node is present in this bond, another node is present in this bond here. Between bond 1, 2, there is one node. Between bond 3 and 4, there is another node that is which we have seen this earlier in the orbital pictures of the various polyene systems. In here, although this is suprafacial and suprafacial with respect to both the components, this leads to an antibonding character in the transition state. So this will be of higher energy in nature compared to this kind of a molecule. So a photochemical suprafacial overlap is a photochemically a forbidden process according to the Woodward Hoffmann rule. So essentially a 2+2 is photochemically allowed when both the components are suprafacial. A 4+2 is allowed thermal conditions when both of them are under suprafacial mode. We can use the orbital correlation method to arrive at the same conclusion as we arrived in the case of frontier molecular orbital method. This is a face-to-face approach of the two ethylene molecules to give a cyclobutene molecule. There are two possible mirror planes that one can consider as symmetry element. Sigma 1, which is a horizontal mirror plane which bisects the newly formed sigma bonds, and the sigma 2 is the vertical mirror plane which bisects the pi bonds of the original ethylene unit. So what we have done is essentially arrange the interacting molecular orbitals. These are two ethylene molecules interacting. In other words, the psi 1 and psi 1 of the ethylene molecule interacting in a symmetrical fashion, the psi 1 and psi 1 of the ethylene molecule interacting in an antisymmetrical manner, the psi 2 of the ethylene molecule interacting in a symmetrical manner and an antisymmetrical manner. This will be in the increasing order of energy in terms of arranging the overlap of the various orbitals of the, and this kind of an interaction is what leads to the formation of the sigma bond. So you have a sigma, you have another sigma bond, you have a sigma star and another sigma star kind of a system is what we have. So there are two sigma bonds formed. So you will have two sigmas and two sigma stars, and these are the overlapping molecular orbitals of the starting points, and these are the overlapping molecular orbitals of the end point. Now all you have to do is look at the symmetry properties with respect to the sigma 1 and sigma 2. With respect to sigma 1, which is a horizontal plane, is symmetric. With respect to the vertical plane also it is symmetric. Here with respect to the horizontal plane it is antisymmetric. With respect to the vertical plane it is symmetric. With respect to the horizontal plane the third overlap is symmetric. The vertical plane it is antisymmetric, and so on. Finally the topmost interaction, which is the antisymmetric interaction of the two antibonding molecular orbitals of the ethylene, essentially is antisymmetric with respect to both vertical as well as the horizontal mirror plane. In the case of the sigma bond symmetry, this is both are symmetric with respect to vertical as well as horizontal plane. With respect to horizontal plane it is symmetric, with respect to vertical plane it is antisymmetric. Here the horizontal plane is antisymmetric and the vertical plane is symmetric, which you can see very clearly. Here both the vertical plane as well as the horizontal planes are antisymmetric with respect to each other. So these are filled molecular orbitals. These are also filled molecular orbitals, whereas these are antibonding molecular orbitals. This is also antibonding molecular orbitals in terms of the orbital interaction. Now the symmetry correlation is very clear that the symmetric combination correlates with the symmetric combination in the ground state. However, this antisymmetric combination, remember this is with respect to sigma 1 and sigma 2, that has to be very clearly specified. One should not confuse that SA is same as AS, because the first alphabet corresponds to the horizontal plane and the second alphabet corresponds to the vertical plane, for example. So this antisymmetric combination is correlated with the antisymmetric correlation of this particular molecular orbital. Similarly, the symmetric antisymmetric combination is correlated here. Finally, the antisymmetric combination is correlated in this manner. You can see very clearly that the correlation is between the ground state and the excited state, which means this reaction has to proceed through an electronically excited state. In other words, this can be possible only under photochemical condition. So a suprafacial cycloaddition reaction of the 2pi type is photochemically allowed and thermally it is forbidden. That is a conclusion that we arrive at. In the case of a Diels-Alder reaction, we set up the pi molecular orbitals of the two interacting component. The only symmetry element that is present throughout the course of the reaction is the vertical sigma, which bisects the carbon number 2 and 3 of the diene and carbon number 1 and 2 of the ethylene, for example. It also bisects in a symmetrical manner of the cyclohexene that is being formed in this particular case. Now, this is butadiene psi 1. And this is psi 1 of the ethylene, this is psi 2 of butadiene, this is psi 3 of butadiene, and this is psi 2 of ethylene, and finally psi 4 of the butadiene. In the increasing order of energy, we have written the molecular orbitals of the butadiene and the ethylene in the increasing order of energy. Here remember there are two sigma bonds that are formed and one pi bond is also formed. So you will have a sigma 1, sigma 2, pi, pi star, sigma 1 star and sigma 2 star. So these are antibonding molecular orbitals which are not filled, and these are bonding molecular orbitals which are filled with electrons. Now clearly with respect to the vertical plane of symmetry, this is symmetric, this is also symmetric, whereas this is antisymmetric, and this is symmetric, this is antisymmetric, and finally this is also antisymmetric. With respect to the vertical plane, this is symmetric, this is antisymmetric, this is symmetric, this is antisymmetric, symmetric and antisymmetric. So when you want to correlate the symmetry properties of the left hand side molecular orbitals to the right hand side molecular orbital, symmetry correlation is very clear between the lowest energy orbitals to be symmetric with respect to each other. And this molecular orbital symmetry correlates with this molecular orbital. Again, filled molecular orbitals are correlated. There is no correlation across the non-bonded level. That means this reaction should proceed under thermal condition. So a Diels-Alder reaction, which is a 4-pi superficial, 2-pi superficial addition reaction, is an allowed process under the thermal conditions and not under photochemical condition. Now the 2-pi cycloaddition reaction we will consider first. These are reactions which are concerted reaction, the convenient way to form cyclobutanes in an organic synthesis. Quite often this is used in the formation of caged compounds also, with cyclobutane rings forming during the course of the reaction. Reaction generally occurs from the singlet excited state pi to pi star state of the olefin. Triplet sensitized is required to form the triplet state of the molecule. The reaction can also take place from the triplet state. We will consider this in more detail when we consider the photochemistry component of this reaction. Acyclic alkenes undergo competing cis-trans isomerization. In other words, if this were to be a trans-2-butene, when you photolyze it, it can also undergo cis-2-butene. We will see that in a few minutes. Reaction is generally superficial addition, and it is highly stereospecific in nature because of the fact that you have a superficial kind of an addition. Now, this gentleman here is Professor R. Srinivasan, who worked in IBM, and he was responsible for the investigation of the cycloaddition reactions of cis-2-butene, trans-2-butene and so on. What he found out was when the reaction is carried out at low temperature, remember these are gaseous molecule and they also absorb in the vacuum ultraviolet region. So these are extremely difficult experiments to do. In addition to that, there is a competing cis-trans isomerization can also take place under the photochemical condition. So the reactions were carried out in the low conversion so that the competing cis-trans isomerization is not a major problem, so that one can figure out the stereospecificities of this reaction. So the credit goes to Professor R. Srinivasan for enlightening us with the investigation of the 2-butene system in this particular example. So if we take cis-2-butene under the low conversion where the cis-trans isomerization does not take place, in other words the pure cis-2-butene undergoes the direct photolysis to give two molecules where the 4 methyl groups are cis with respect to each other. Here the 2 methyl groups are cis and this is anti-cis. So this is cis anti-cis is what we have. We will just call it as the syn isomer here and an anti-isomer here in terms of the nomenclature that we are talking about. So this is formed in about 0.8 ratio. The syn isomer is formed slightly higher than the anti-isomer, for example. So you can see here by following the thick line, the cis-2-butene component is approaching phase to phase. This is also approaching phase to phase, except that it is an anti-phase to phase kind of a approach is what we have. Here is the trans-2-butene component. The trans-2-butene components are very clearly given by the thick lines. So here a head-to-tail approach is what is happening. Here a head-to-head approach is what is happening. Remember, these two are common products. These two structures are essentially identical structures and they are common product in the cis as well as the trans isomer. These two isomers are different in the cis and the trans with respect to each other. When a mixture of cis and trans are taken, when a mixture is taken and photolyzed, for example, in addition to these three products, that is product 1, product 2 and product 3, in addition to all these three products, there is a unique product formed which is a combination of the cis and the trans olefin which is undergoing the cycloaddition reaction in this manner. So this essentially illustrates and confirms the stereospecificity of the cycloaddition reactions proceeding through a superficial cycloaddition process with the retention of stereochemistry of the olefin, which is shown in the thick lines in the cyclobutene that is being formed in this particular case. These are some more examples of the 2+2 cycloaddition reaction. Ethylene reacts with maleic anhydride, for example, at minus 61 degrees, because ethylene is a gas, it needs to be condensed at low temperature. Essentially, a 2+2 cycloaddition reaction is what is taking place to give this particular product. Here is an interesting example of an exciplex formation. Exciplex formation is nothing but the excited state complex. In other words, if one olefin is in the excited state and it forms a complex with another olefin, you call it as an exciplex. Exciplex are excited state complex where the two components are different. One of the component is in the excited state, the other component is in the ground state. In this particular example, this molecule is excited. It goes to the excited state and it forms a complex with the tetramethylethylene, for example, and the complex probably is a sandwich type of a complex. It immediately undergoes a cycloaddition reaction to give the cyclobutane formation in this particular case. The quantum efficiency of exciplex formation is nearly 1, and hence the formation of this particular product is also very efficient in this photochemical process. Now the trans-stilbene can undergo cis-trans isomerization as well as it can undergo the cycloaddition process. In the cycloaddition process, you can see here there is a 4:1 ratio of the syn-anti-syn product is formed here. This is the trans, this is another trans molecule. Here this is the head-to-head approach, head-to-tail approach, whereas here is a head-to-head approach in terms of the approach of the two molecules. Both the molecules are possible to obtain from the trans isomer of the stilbene molecule. When the trans-stilbene is tied up in the, this is also you can consider to be a rigid form of a trans-stilbene. If we consider this benzene ring connected to this olefin and the other benzene ring, except it is a fused form, unlike this form where you have a benzene ring connected to a double bond and connected to the benzene ring. This is a conformationally flexible system, whereas this is a conformationally rigid system. In the rigid system, the central double bond undergoes the 2+2 cycloaddition reaction with this particular diester, essentially giving this product in about 51% yield. The dimers of the individual components are also formed to the extent of about 20% or so in this case. Now the cis-trans isomerization is not a problem when you have a cycloalkene, particularly cycloalkenes of the smaller ring sizes from 3 to 7. So no cis-trans isomerization competes with the cycloaddition process in the case of cyclic olefin. Therefore cycloaddition is efficient. There is no energy wasting in the cis-trans process. Simple alkenes absorb very poorly in the 200 to 250 nanometer region. Therefore, a triplet sensitizer might be useful. Typically, triplet sensitizer with energy above 75 kilocalories per mole is ideal to promote this kind of a reaction. In other words, sensitizers are essentially photocatalysts. They will absorb the light energy and transfer that light energy to the olefin. By themselves, they are very poor absorbers. So it helps to transfer the energy from one molecule to another molecule to make them excited, to go to the excited state, for example. That is accomplished using a triplet sensitizer, provided the triplet sensitizer has a higher energy than the triplet state of this particular molecule. These are examples of simple olefinic system undergoing 2+2 cycloaddition reactions. Cyclopentene, for example, undergoes cycloaddition process to give all cis hydrogen. In other words, this is a cis fused dimer of the cyclopentene. This is a cis anti-cis kind of a isomer of this. The thick dot essentially indicate that there are 4 hydrogens and all the 4 hydrogens are above the plane of the cyclobutane ring here. In this case, these 2 hydrogens are above the plane of the cyclobutane ring, and there are 2 hydrogens here which are below the plane of the cyclobutane ring. Cyclobutene itself undergoes the cycloaddition process, 2+2 cycloaddition process, to give a Laderian kind of a system. A tricyclic system is what is formed. Norbornene, for example, undergoes sensitized, photosensitized cycloaddition reaction. This is a triplet sensitizer, acetophenone. So it absorbs the light energy and then transfers it on to the norbornene. Norbornene then undergoes a cycloaddition process to give 2 types of products depending upon how initially the 2 olefins are oriented with respect to each other. You can see here, for example, this is a head-to-tail kind of orientation. Anti-orientation is what is taking place, whereas here you have a syn orientation with the 2 bridges forming in the same direction, for example, in this particular case. This is acinaphthalene. Acinaphthalene undergoes cycloaddition process to give head-to-head or head-to-tail kind of a syn and anti kind of a isomer. and depending upon whether you have a singlet sense, direct photolysis gives a 4:1 ratio of these two products, probably forming through an excimer kind of a system where the two olefins are coming parallel with respect to each other to form an excimer and then collapses to give the cyclobutane ring here. Alternatively, when it is carried out in N-propyl bromide, this reaction proceeds through a triplet state because the heavy atom effect causes the intersystem crossing to take place. We will discuss all these things in detail under the photochemical condition, under the photochemistry topic, not under pericyclic topic. So assume that this reaction is proceeding, one is proceeding through a singlet state, the other one is proceeding through a triplet state. The ratios seem to depend upon the state by which the reaction is taking place in these two cases. Here is an interesting example of an intramolecular 2+2 cycloaddition reaction. All of them are in fact intramolecular 2+2 cycloaddition reaction. This molecule has a curvature that is responsible for the intramolecular cycloaddition reaction. Narbornadiene undergoes 2+2 cycloaddition reaction intramolecularly. In other words, these pi bonds are facing in this direction. The other pi bonds are facing in the other direction. So there is a possibility of overlap of the lobes of the pi system from this side to this side, essentially forming a sigma bond. This is called quadricyclane. This is a highly strained system. This is a high energy molecule. This is not thermally stable. When you heat it, it goes back to the narbornadiene as the product. In this case, again, this is a larger system. This is a 2-to-1 bicyclic system, whereas this is a 2-to-2 bicyclic system. Here also the quadricyclane kind of a compound is formed readily when the photolysis of this kind of molecule take place. Here is an intramolecular version of the 2+2 cycloaddition reaction. Cyclopropene is a very reactive molecule in the excited state. It undergoes cycloaddition reaction, for example, to give the cyclobutane. This is the newly formed cyclobutane. So originally you had a cyclobutene here with the 6 carbon attachment, that is 3 plus 3, 6 carbon. This is how many methylenes are there? There are 3 plus 4 methylenes are there. 1, 2, 3, 4. So this is originally a olefin, that is the terminal olefin of this cyclopropyl derivative. So the cyclopropane is still intact. This newly formed cyclobutene is fused with the 6-membered ring. The 6-membered ring is arising because of the long chain which has the 4 carbon plus the 2 carbons of the olefin, resulting in the formation of the 6-membered ring. So this is intramolecular version of the cycloaddition reaction is what we are referring to here. These are some interesting examples of how to make caged compounds using cycloaddition process. Caged compounds representations are given here. This is bis-homocubane. If these two methylenes are not present, then you would call it as cubane. If you form a bond between these two carbons here and these two carbons, that would be cubane. This is 2 carbons more than cubane, so it is called a bis-homocubane. Now this is a dimer of cyclopentadiene. The dimer of cyclopentadiene is a endo-isomer is what is taken. These two olefins are in close proximity because of this curvature that we talked about in a few minutes back. The same is true in this molecule also. This curvature causes this pi bonds to come in close proximity to this pi bond. So intramolecular 2+2 cycloaddition reaction is very facile. So the newly formed cyclobutane derivative you can see here. This is the newly formed cyclobutane molecule that is given here by an intramolecular 2+2 cycloaddition process. Now this is a molecule which is formed by a cycloaddition reaction, which is a Diels-Alder reaction from cyclooctatetraene and maleic anhydride. We will see that later. These two pi systems are facing parallel to each other. This is the most convenient geometry of the molecule to undergo a 2+2 superficial cycloaddition reaction. It does undergo 2+2 cycloaddition reaction to form the cyclobutene that is shown here. This cyclobutene is formed by a 2+2 cycloaddition reaction. This molecule is hydrolyzed and then it is made to undergo oxidative decarboxylation using lead tetraacetate to give what is known as basketine. This molecule is supposed to be a basket where this is the handle and this is the basket part of the molecule. Now pentaprismine is an interesting molecule. This was synthesized by Phil Eaton, and this is essentially carried out by a face-to-face 2pi cycloaddition reaction of this particular acetal of the ketone, which is this particular ketone. This ketone is now decarbonylated to give essentially the pentaprismine molecule after a few steps. So the crucial step is the formation of the cage by forming the cyclobutane derivative, which is this particular cyclobutane derivative, and that essentially results in the synthesis of the pentapyrazamine. This is Professor Mehta, who is the former director of the Indian Institute of Science, Bangalore. He has made several contributions in the 2+2 cycloaddition reaction, and he is responsible for the synthesis of the bis-homo-hexapyrazamine. Hexapyrazamine is a molecule where you have a bonding between these two carbons and these two carbons, divide of these two methylene units, for example. However, that molecule could not be synthesized. The bis-homo-hexapyrazamine has been synthesized. This is essentially by a phase-to-phase 2pi cycloaddition reaction of this olefinic compound to give the cyclobutane derivative. From here, the decarbonylation followed by the cycloaddition here essentially leads to the formation of this 4-membered ring. So this is a very elegant synthesis of the bis-hemocubin that is given in this particular slide. Here is another example of synthesis of hirsutane. Here is a cycloaddition adduct of cyclopentadiene with the benzoquinone molecule. This is a Diels-Alder adduct of cyclopentadiene with the quinone molecule. That puts these two double bonds in close proximity to each other. The face-to-face separation here because of the curvature of this molecule, essentially because it is an endo-adduct. This comes in close proximity to this particular double bond, resulting in the formation of the 2+2 cycloaddition reaction. Now the newly formed bonds are this vertical bonds, which is a cyclobutane bonds. Now if you cleave the horizontal bonds in these bonds, for example, the slanting bonds, you will essentially open up this molecule. So to give a 5-membered ring, 5-membered ring and 5-membered ring fused system, and these are all cis-fused by 5-membered ring system. Essentially this was converted to a natural terpene called hirsutene, and these reactions were carried out in the laboratory of Professor Mehta. Finally, last example of two benzene units, because of the rigid structure of this bicyclic system, the two benzene units are essentially face-to-face. Benzene normally does not undergo 2+2 cycloaddition reaction because it doesn't like to lose aromaticity. However, this is a special case where the two benzene are coming face-to-face within a short distance of about 3 angstroms or so. So that photolysis of this molecule essentially led to the formation of a 2+2 cycloaddition reaction. Interesting caged structure is what is being formed here. Here, the 2+2 cycloaddition reaction is prompted by the spacer unit, which is the 2,2 paracyclophane unit. The distance between the two benzene rings of the 2,2 paracyclophane unit is about 3.5 angstroms or so. Anything that is less than 4 angstroms separation between two double bonds of this parallel double bonds will undergo cycloaddition process, for example. So the 3.5 angstrom separation spacer is a very useful spacer. So this diene essentially undergoes cycloaddition reaction with the diene which is parallel to this. This is called a pseudo-geminal isomer of the disubstituted paracyclophane derivative. So that gives a ladderane kind of a structure. 2+2 cycloaddition reaction between this diene and this diene essentially gives these 4-membered rings, resulting in the formation of a ladderane kind of a structure in this particular case. Very interesting example of 2+2 cycloaddition reactions are shown here. So what we have seen in this module is the definition of cycloaddition reaction, the various types of cycloaddition reactions, the analysis of the cycloaddition reactions using frontier molecular orbital method for the 2+2 as well as 4+2, the orbital correlation method for the 2+2 and the 4+2, and then we see a lot of examples of 2+2 cycloaddition reactions which are intermolecular as well as intramolecular type. I hope you enjoyed this session. Thank you very much for your attention.